All right, so today we're going to talk about the scientific revolution. Now, of course, this is not the same kind of a revolution like a political revolution. This, of course, is an intellectual revolution, a revolution of ideas. Now, and this takes place in Europe. So, one of the reasons that Europe becomes, I think, one of the leaders in the world and expand all over the world is because they are using science and developing technology. So to understand why did science develop in Europe at this time, we need to take a look and see that a lot of things are changing from, say, the old medieval way of doing things. One of the changes was the way they looked at the world. The church, and what we're going to see is the church, and by that I mean primarily the Roman Catholic Church, but there really only was one church at this point. That church had taken the sort of scientific ideas of its time, the teachings of Ptolemy. Ptolemy was a Greek, actually, who lived in the 2nd century BC, so say around 180 BC. Ptolemy had an idea of how the universe was constructed. So you might call him a Greek astronomer, a Greek sort of mathematician. But his view is often called geocentric. Why? Well, see, the word geo means the earth, like geology is the study of the earth, and centric, in the center. So his idea of the universe, of the solar system, the universe, everything that's out there, is that the earth was in the center. The earth is in the center, and everything else revolves around it. It's like a lot of people that you meet. They believe everything revolves around them. Of course, no one in this room. I'm not talking about anyone, but they think everything should revolve around them. Anyway, enough of that. He believed the earth's in the center. Now, the church ended up adopting this view. Was it, like in the Bible? Well, not necessarily in the Bible, but they felt it fit the Bible's model. And so they took a prevalent view. The church didn't come up with this view, but they took the view and then they made it doctrine. They made it official teaching that the earth is in the center. Well, doesn't it make sense? Say, let's just sort of think biblically a little bit, or try to. Shouldn't the earth be in the center? Didn't God focus his attention on earth? Creation, the whole creation story is about the earth being formed and what happens on the earth and how people are made on the earth. Didn't God set his sun where? Not to Jupiter, not to Mars, but to the earth. The earth is at the center of God's attention. So the assumption was the earth, it makes sense that the earth is in the center of what God created. Well, I don't know if they... Well, yeah, Copernicus, we're going to talk about Copernicus. Copernicus didn't really, he was a smart guy. So he didn't really even announce his views till he was dead. That's one way to avoid trouble with people. That's why I try not to talk too much, except in class. So yes, Copernicus, you are right on the money. So here is Ptolemy's view. Here is our buddy Copernicus's view. Now, Ptolemy's view, probably somebody you know, maybe your mother, your grandmother, I don't know, your third cousin twice removed, whatever that means, has a set of bowls. Imagine a set of mixing bowls. They're glass. They're clear. And you know how they do? One fits inside of the other, right? You got one that's about this big, and you got one that big, and that big, and that big. Makes it nice to store. You put them up in the cabinet, one inside of the other. Now imagine you took those clear glass mixing bowls, you put them out on a table, and you flip them over so that they're one inside of the other and they're sitting on the table, but you can see through them. That is Copernicus's view of the universe. Then imagine on those clear bowls, for example, you put something in the middle there, the Earth, put a bowl over it. Maybe on that bowl you paint some stars, a planet. And now imagine that you have it on some kind of device where you can move those bowls individually while the middle stays stable. I don't know if I'm explaining this very well, but that's the way he saw the universe. The Earth was in the center. Everything revolved around it, but is revolving at different sort of speeds and also at different levels. You ever heard of the seventh heaven? The 7 levels of heaven? That's what they're talking about. That you have the planets at one level, you have the stars, you have the sun, you have the moon. These are all at different spheres or different levels, and they're spinning around the Earth. Here's the Earth. And the very outer one is the firmament, right? The stars. All right, so that was the view that Ptolemy came up with in the 2nd century BC. Greek thinker, mathematician, astronomer, if you will. Okay, now comes along Copernicus. Copernicus puts the sun in the center. Puts all the planets spinning around the sun. The Earth being the third one, the third rock from the sun. Right? And it goes all the way out to, well, he didn't have 9 planets there, but you can see what he has, right? Now that may seem like, okay, it looks pretty similar, right? What's the big deal? It's a very big deal because it reorients the whole universe. It reorients everything. Here's our buddy Copernicus, 1473 to 1543. His most famous work, his writing, On the Revolutions of the Heavenly Spheres, 1543. In this, of course, he describes what I just tried to show you there in a representational form, the sun in the center. Many rejected this. I think that's probably an understatement. Most people rejected it, and many people felt that Copernicus was going not only against commonly held scientific ideas, but he was going against religion. He was going against Christianity. Why? Because the church had officially adopted the view of Ptolemy. And to say that the Earth was no longer in the center was then seen as a challenge to the idea that the Earth was a special place in which God had done special things. Special creation. Right? Sent his son. God sent his son to the Earth, didn't send his son to Mars. God made life on the Earth, didn't make life on Jupiter. You see? And so here's the thing. Imagine if you're on the Earth. Oh, well, you are, so that might be easy. You are on the Earth. Prior to Copernicus, you were at the center of God's attention. The Earth's at the center of God's attention. You're on the Earth, and God made this place for you. Now, if you take Copernicus's idea that the Earth is just a planet circling the sun, which is a star. He's not even talking about many, many other stars, but you're just one of many planets out there, one of many spheres that are circling, and you're not even the biggest one. The Earth by far is not the largest planet. Suddenly the Earth's not as important. And guess what? If the Earth's not as important, then maybe we aren't as important. It calls into question presuppositions. You see what I have down there? Rethinking of presuppositions. Do you have any presuppositions? Maybe you never thought about it. If you have one, can you name one? One of your presuppositions? I know, you just ate lunch. You had some of that taco salad or whatever, right? Didn't you have a taco salad? Yeah. Hard to go from taco salad to philosophy or something. But you know, what is a presupposition? Yeah. Yeah, it's an idea. It's a supposition. It's a thing that you assume, a thing that you hold to, and it sort of frames everything else, right? For example, just looking around the room, I would say most of you are what some people would call naive realists. What? A naive realist. A naive realism, in a philosophical sense, means that you believe that what you see is really what is there. That your perception is a true perception of reality. Well, that's what most people think, right? I say, oh, see that bottle sitting there? I assume, there's a lot of assumptions in that. I assume you know what a bottle is. I assume you're seeing the bottle, that I'm seeing the bottle, and that what I'm seeing is really there. So therefore, you can also see what it is that I can see. You might not think there are any presuppositions in that, but it's loaded with presuppositions. That what I see is really what's there, and that what I see is also what you can see. And not only that, we can communicate it and agree upon it. Well, it's not a philosophy class, so be thankful for that. Or we'd have to talk a lot more about that. So a presupposition then is the idea. Take, for example, maybe you have a presupposition that God exists. There is a God. Maybe you have a presupposition that God is good. Because just because God exists doesn't necessarily mean that God is good. God might be bad. We don't even like to say it, right? But God could be bad. Or you might probably have a presupposition that God kind of knows what's going on, but maybe you could imagine a God that doesn't know what is going on, right? Well, anyway, a lot of presuppositions. So what begins to happen then, since we've had this presupposition that the Earth's in the center, everything revolves around it, and now all of a sudden Copernicus messes this all up for us. And we have to think, hey, wait a minute, what are you talking about? The sun's in the center. It made people begin to question everything. Question all their presuppositions. How do I know what it is that I know? For the philosopher, this is called epistemology. Epistemology means how do you know? The study of how you know what it is you know. And again, since this is not a philosophy class, we're not going to go into that too much. But this shakes everybody up. That's what I'm trying to tell you. I put this up here for fun. You know, if you have a twisted definition of fun like I do. This is a reconstruction of what Copernicus looked like, or what they believe he looked like. How could they make this? Well, they took the skull. There's a body. It was buried in a cathedral. People believed it was Copernicus. Some people questioned whether it was. They took a DNA sample from the bones, from the teeth, and they compared it to DNA found in the hair that was found in a book that belonged to Copernicus. So So they assumed some of his hair fell out while he was reading his book, I guess. They compared the two DNA and it was the same. So the guy that owned the book was the guy that was in the grave. And they believed that to be Copernicus. So then they took the skull of the guy in the grave and they got some of those forensic people, sort of work on murders and stuff, to recreate what he looked like based upon his skull. So I would say, do we know exactly what he looked like? Well, we got pretty close. I bet Copernicus's friends, if they saw that, they could tell you that was him. Maybe the eye color's not right. Maybe the hair is not quite right. Well, I'd say that's pretty close. That's about as close as you're going to get. So you can see it down here, down below, how they did it. So I thought it was just fun. Copernicus, I just put it in there. All right, let's move on. Let's talk about some other guys, like Johannes Kepler. Yes? Yeah, he was in a church. In churches in Europe, they often bury people inside the church, in a crypt or in a grave. And so this grave was marked. They thought it was Copernicus, but they weren't sure. And so the best place to get DNA out of a skeleton is from the teeth, because it tends to survive better. Yeah. So they compared that with the hair. All right, let's talk about our buddy Kepler, Johannes Kepler, 1571 to 1630. Many people ignored Copernicus's ideas. Why? Well, they were so revolutionary, they were so controversial. Remember, I told you, Copernicus had this stuff figured out ahead of time. He wrote it down, but he did not publish it. He left orders that when he died, that it should be published. What was that, 1543? So it's not published till 1543, the same year that he dies. Not a coincidence. Copernicus did not want to deal with the church, giving him grief. He knew they would. So, after he's dead, they want to excommunicate him. Okay. Go ahead. I mean, it can't stop him. But he just didn't want to have to, go to jail. He don't have all the controversy. And so he said, you know what? I'm leaving this. And he told his family, when I die, tell them to publish this. And they did. All right. So Copernicus's ideas were known somewhat, but ignored or shunned because it was thought to be too controversial. So along comes a guy named Kepler. Kepler is a brilliant mathematician. And he begins using the work of Copernicus then to further that work. I bring this up for a couple of reasons, but at least one of them is that we should build upon one another's work. In other words, you don't have to go back and reinvent the wheel. Somebody already invented the wheel. Can you make the wheel better? Maybe. But why go back and start from scratch? Right? And this is what science is built upon. This is what research is built upon. In any academic discipline you do research, you're doing that based upon what other people's research was. And so you try to use their research to further your own. Well, this is what Kepler did. When he began to examine Copernicus's ideas, and he was particularly interested in the motion of the planets, and he worked on this mathematically, his calculations confirmed what Copernicus had worked on, but there was one problem that he noted. Copernicus, if we go back to this, I'll come back to this. Let me just go back to the picture here. Notice that Copernicus has circular orbits for all the planets. They're very circular, right? All right. When Kepler began to work on that, he figured out that the orbits could not be mathematically circular. that they would in fact be elongated, elliptical. Okay? And that made sense mathematically. Well, again, when it's not a science class and not a philosophy class, but if you swing something, you have a heavy object and it's going around it, it's a centrifugal force, but it's going to tend to have an elliptical orbit rather than a purely circular one because of the motion of the planet and the weight, the mass of the planet. Anyway, he worked it all out. So what I'm saying is he confirmed what Copernicus had said. He modified it, refined it, and said, well, here's the problem. They're elliptical orbits. And here comes another guy, Galileo Galilei, 1564 to 1642. Here we see a portrait of Galileo in the lower left of the screen. In the upper left of the screen, you see a telescope. Galileo actually created, made, invented his own telescope so that he could look at objects out in what we would call space, out in the heavens. He used two lenses to magnify. So this is called a refraction telescope because the light comes in, it's refracted, and then focused by another lens. So sort of magnified and then focused. As he began to use this, he began to look at the different heavenly bodies. He looked at the moon, studied the moon. He actually saw mountains on the moon. He began to draw the moon, and he even named some of the mountain ranges, right? Some of the features. The Sea of Tranquility, for example. He then turned his telescope towards Jupiter. Not only, of course, could he see Jupiter, but he noted what some people had never noted before, that there were 4 moons that he could see circling Jupiter like our moon circles the Earth. He turned his telescope towards the sun, where he saw sunspots and solar flares and these dark spots on the sun moving around on the surface. Now, by the way, just a public service announcement, don't stare at the sun. Don't get binoculars, telescope, whatever, or you can just stand out there and stare at the sun looking for solar flares. This is what caused Galileo to go blind. He didn't know that it would. He found out. By the way, we had a total eclipse of the sun a few years ago. When was that? 3-4 years ago? Remember that? There are people who went blind because they didn't follow the rules. They stared at the sun, and you could stare at the sun more easily when it's on an eclipse because it's blocking out, the moon's blocking out a lot of the light, but you're still getting the radiation. So some people had their eyesight greatly diminished. Some people actually lost their eyesight by staring at the sun. Maybe, yeah. He also determined that the universe was not made up of the same stuff as the Earth. That's what we call space. We know that space is basically a vacuum. The atmosphere around the Earth is not out there in space. Okay? So that makes it different. So when you get up in space someday, before you jump out of the spacecraft, well, make sure you have a suit on. Otherwise, you're not going to last very long. You'll kind of explode or implode. Well, anyway, it won't be good. The gases in your body will be sucked out of your body. Let's not think about it. We just had lunch. Anyway, so he writes all this down in a work that he calls the Starry Messenger. And in this, of course, he is saying that the message that he's receiving is coming from the stars, coming from the heavens, and that the heavens are teaching. He's no atheist. He believes in God. He's a Christian, but he sees these things and he reports them. He sees it as a message, a revelation, if you will, from the heavens. He publishes it in 1610. Now, one thing he did not learn from Copernicus, he didn't wait till he was dead to publish his stuff. So when he published it in 1610, he was immediately arrested, put on trial, and found guilty of Copernicanism. Well, it took a little while because they wanted to give him a chance to take it all back. And, first he said, no, I'm not going to take it back. Eventually he did take it all back. He said, no, I was just kidding. I didn't really mean it. But then before he died, he said, no, I wasn't kidding. So, yeah. So keep that in mind. Galileo had to, Copernicus just avoided it by waiting until he died. Galileo had to deal with it and finally backed off. And then had take-backs, right? What do you call it? Take-backs? No take-backs? Well, anyway. Now comes our buddy Isaac Newton. Born on Christmas Day, 1642. And he has some of the most impressive hair of this period. Well, anyway, maybe it's a wig. So we see Isaac Newton was one of the key people in the scientific revolution. In 1661, he attends Cambridge, and he will graduate. By 1669, he's named chair of the math department at Cambridge. Isaac Newton was a genius. There's no doubt about it. We kind of throw the word genius around pretty loosely these days, but I think by any measure, Newton was one. But of course, he would say that he did not get all of this in isolation. He used the work of Copernicus, Galileo, Kepler, and certainly probably others, and he built upon their work and came up with his own ideas, okay? Some great discoveries that are going to change the way people think about the world, and, by the way, we still use them today. What are those ideas, you say? I'm glad you asked. You say I didn't ask? Well, I thought you would. Well, what are some of his great discoveries? Well, one of them is dealing with light. Newton really was fascinated by light, the study of light. He came up with the idea that what we would see as, say, daylight, right? Daylight, or white light, or just regular light, was actually made up of many different colors of light. Have you ever met Roy G. Biv? You must have met him at some point, right? Roy G. Biv, Mr. Biv. Remember what they are? Red, orange, yellow, green, blue, indigo, and violet. Okay, Roy G. Biv. Don't mess up with Roy G. You don't want Roy Biv. Roy Biv. Roy G. Biv. Anyway, so if you take a look at what we have up here, a prism, you could take daylight, light's just coming into from the outside, let it hit a prism like this, it gets bent, bounces off, and it bounces off on the wall or whatever as a rainbow in those colors. And always in those order, by the way. Roy G. Biv doesn't mix up his colors. You never put the green at the end. The green's always there in the middle. All right. So you have the rainbow, as we would call it. And of course, that's how a rainbow is formed. Sunlight comes through the water droplets, which then creates the rainbow. All right, he kept studying light. He said, okay, light can be sort of white or clear. Light can be these different colors. But light travels much like a particle, much like you took a ball and threw it. Right? If we had a mirror and the light came through the window and hit the mirror, it would bounce off the mirror in a straight line and bounce off another wall or something, right? Much like a rubber ball. If we threw it at an angle, it would bounce off at an angle. But also, light moves like a wave. It has a wavelength and so forth. Anyway, so he really began to examine light. Wavelengths, particles, colors, and so forth. If you've ever taken calculus, and I hope you have, you can blame Newton, because he was the guy who really came up with that idea. And the idea, the basic idea of that is taking mathematics and putting in the element of time, infinity. So that becomes another factor in the calculations. So that's calculus. He develops a telescope, but his telescope is a reflection telescope, not a refraction telescope. A reflection telescope is actually more powerful, can be far more powerful than a refraction telescope, because it actually is formed with a mirror, a parabolic mirror. That is a mirror like in the shape of a bowl, a curved shape of mirror. The light comes in and hits that mirrored surface, which would then focus the light into the center of that bowl area, right? And that's where you put the eyepiece with another little mirror that bounces it up in an eyepiece you can adjust. That's basically it. A tube with a parabolic mirror and an eyepiece, usually with a small reflective mirror at the focal point. This actually gives you far greater magnification. It can give you far greater magnification than a refraction telescope. Newton also comes up with, he's a creative guy, the laws of motion. We still use these laws of motion today. For example, you must have heard some of these before. An object in motion tends to stay in motion, and an object at rest tends to stay at rest, unless the object is acted upon by an outside force. So take the balls on a pool table, right? They just all sit there until you take the cue ball, whack against those other balls, and then they scatter and go in different directions. Why? Because you hit the ball with a force, and then that ball hit another ball with force. Well, here's a more practical one, with well illustrated. Take a look at this. Okay, let's say, for example, you're driving down the I-4. All right, and you're doing your typical, 90 to 100 miles an hour on the I-4. And you come to some kind of an overpass or some kind of object there. Your car hits the object. the object doesn't move because it's very heavy. Your car stops moving. So, the car is at motion. It's acted upon by another object, which let's say is the wall. And let's say you, as is typical, you don't wear your seatbelt. So when you're moving down the highway 60, 70, 80 miles an hour, your car is going that fast, but you are also going that fast. And if your car stops suddenly, you're going to keep moving that fast. That's why you wear a seatbelt. So here's what happened to this guy. He goes right out the windshield. See that? I don't want that to happen to you. So wear your seatbelt. Okay. So that means an object in motion tends to stay in motion. You're going 80 miles an hour and the car stops all of a sudden, you're going to want to keep going. That's the first law of motion. Second law of motion. Second law of motion is acceleration equals force divided by mass. All right, here's our hippie. And here's the hippie van. Probably a VW van. Right? So the hippie ran out of gas. So he's got to push the van to the next gas station. So that's what we're talking about, acceleration. How fast can the hippie get the car going here, the van going? It's dependent upon its mass. That is, it's what typically we call its weight, although mass is a little different than just weight. But let's not go into that right now. And the force by which he pushes it with. This will yield the acceleration. Now, good thing about the van is it got 4 tires that are all inflated. Otherwise, this would change the whole thing. That's the second law of motion. Here's the third law of motion. Every action has an equal and opposite reaction. Do you see what Newton's doing here? He's going through and analyzing the whole universe, really, the world around him. What he sees, what he observes. And he makes up laws. He makes up rules for it. Why do you think we can have rules like this? Why is it that every action has an equal and opposite reaction? What if today it doesn't want to? What does this assume? That there can be laws. Yes? Yes, uniformity. Yes, you went right there. Regularity, uniformity, consistency. And yes, God. Since God stays the same. We read this in this book called the Bible. If you haven't read it, I recommend it to you. There's a book called Hebrews, Letter to the Hebrews, where it says God is the same today, tomorrow, yesterday, today, and forever. God is the same. God does not change. Since God does not change, we have a constant in the universe. You know, it doesn't seem like much, but everything in your life changes. Everything changes. The older you get, the more you'll realize it. Nothing stays the same. You change. The people around you change. The world changes. Society changes. Everything you own changes. It gets older. It wears out. It breaks. Right? But God doesn't change. Now, if God created the universe, and God is consistent, the presupposition here is that the universe is consistent. That God made the universe in a consistent way. So that if I drop this, every time I drop it, it's going to go down. It's going to fall. It's never going to go whoop up. It's never going to go way over there. It's not going to just float. Why? Because the universe is consistent. This has a slight amount of mass, and we have a force upon it, which which we call gravity. That's going to draw it towards the earth every single time. That's a consistency. Yes, Newton is working from the presupposition that God exists and that God's creation reflects God and that God is consistent, therefore his universe is consistent. And if that's the case, then we can have laws. Things do work this way. You know, the Greeks didn't believe that. You ever read any Greek mythology? Greek gods are unpredictable. Greek gods do whatever they want. Greek gods are a lot like people, except more powerful. They get angry, they get mad. And you know what? People are not very consistent. People are not very logical all the time. They're very emotional. They get caught up in stuff. They do things that makes no sense, really, logically. It makes sense to them emotionally, perhaps, right? But God is not like that. And so then Newton says, okay, that's the way the universe is going to work. It's not that, oh, well, you know, gravity's having a bad day, so he's decided he's going to sleep in. No, gravity works all the time. He could be your friend, he could be your worst nightmare. It just depends on your situation. All right, so here's the guy. He had an action. What I want you to look at is the size of that guy's fist in that drawing. I mean, his fist is about more than about a half what that guy's head is. That's a pretty big fist. Anyway, the guy whacks him in the head, in the face. What's going to happen? Well, his head's going to move backwards from the force. What happens after that, I don't know. Maybe the guy passes out. Maybe the guy gets really mad and starts swinging at the other guy. Maybe the guy's got a weapon. I don't know what happens. Make up your own story. But for every action, there's going to be an equal and opposite reaction. Well, there's a lot more of these rules. We're not going to go through all of his laws of motion. But he comes up with laws of motion. He comes up with laws of gravity, the law of gravity. I mean, it's not that he invented gravity, but he recognized gravity, or a force that draws things to Earth, and then he created a law. Of course, according to the story, he was sitting under an apple tree and just kind of relaxing, and then an apple fell off the tree and hit him in the head. And he goes, "That's it! Eureka! There is gravity." All right, well, I don't know if it quite worked that way. But this comes from, they used to have little after-school cartoons on science and language and stuff. It was called Schoolhouse Rock. You'll have to Google it sometimes. They have some pretty good jingles about different things, about government and science and language. That's where this is from. So this is the Isaac Newton cartoon of him. Well, anyway, he comes up with all of these ideas. Laws of motion, laws of gravity, and all how these things work with astronomy. And we see then that he writes it down in the mathematical principles of natural philosophy, usually just called in the Latin by the first word here, Principia. Principia Mathematica, 1687. But in it, he believed that God held the universe together and that God had set the objects in motion. Because we see things in motion. And remember what he said, once they're in motion, they tend to stay in motion. But how did they ever get in motion? Now, some others take Galileo's ideas, but they reject his view of God, at least a personal God, and they begin to see the world like a machine. The world like a machine. So some people started to call this, and certainly not so much Newton, but those after him, would call it the Newtonian world machine. But this all comes about by using the scientific method. The scientific method, then, is based upon observation. You observe whatever you see happening. The apple falls from the tree, hits the ground. You observe other things falling, and it seems to be consistent. So then you have to define a problem. And then you form a hypothesis, an idea to explain all of this. And then you have to experiment. Does everything fall? How fast does it fall? Do you know? Let me ask you this. If I dropped something that weighed 2,000 pounds and I dropped something that weighed 2 pounds from, let's say, a mile high, which one would hit the ground first? Okay. Let's say they're both spheres of the same size. They're the same. They'll hit the same. So 2,000 pounds, if it's the same size and shape, would hit the ground the same as a 2-pound object. Is that what we're saying? Does everybody agree? Is it a trick question? I never ask quick trick questions, do I? I don't think so. I don't know. Maybe I fool myself. Well, Galileo, for example, experimented with that. There's a place in Italy called Pisa. Have you heard of it? Not pizza. Pisa, P-I-S-A. And it has a leaning tower. You ever heard of the Leaning Tower of Pisa? The Leaning Tower of Pisa, Galileo went up the Leaning Tower because it's leaning like this, and he dropped stuff off of there because it's easy to drop stuff off of there because it's leaning. Well, I've been up to the top. Sometimes I don't know if they let anybody go up there anymore. But they built the tower. The tower started to lean, and then they built a piece on top of it to try to balance it. Anyway, next time you look at it, take a look. There's kind of a piece up there to try to, get it to lean back the other way. Anyway, he dropped it. Things of different weights. And yes, they both hit the ground at the same time. So when they got up on the moon, the astronauts decided, because what Galileo had said was that a feather and that a rock would hit the ground at the same time if it wasn't for air resistance. And so they took a feather with them to the moon. And they dropped, maybe it was a hammer, maybe one of their hammers or a rock, and the feather. Ground at the same time. So Galileo would be happy. Okay? And there's also a maximum, did you know this? There's a maximum speed that you would get to. Say if you jump out of an airplane, you're not just going to keep going faster till you hit the ground because your parachute doesn't work. You rest assured, you will not hit the ground any faster than 9.8 meters per second squared. That's the terminal velocity of any object falling in the earth. So, it's still going to kill you. But, at least you won't be going like 1,000 miles an hour. So, here's our scientist. Look, he's doing this. Well, the scientific method and Newtonian ideas reign until the time of Einstein. 20th century, Einstein comes up with his theory of relativity. But I can tell you that on the everyday level, you still use Newtonian physics. If you want to calculate speed, velocity. For example, you're out here and you have an accident. I hope you don't have an accident with a car, but if you have an accident with a car, and the police show up, they're going to write their report down. They're going to ask you how fast you were going, and then they will calculate it. So if you got a big skid mark of rubber there, they're going to measure it. You measure that skid mark, and they'll be able to give a pretty good estimate how fast you were going. It'll underestimate it. But if you say, "Oh, I was going 35 miles an hour," and they look at your skid mark, they say, "No, sir, you're going at least 65 miles an hour because of that skid mark." Because of the coefficient of friction of the rubber against asphalt or concrete. Take the weight of the car. You can figure it out pretty closely. Anyway, that kind of stuff we're still doing today. Francis Bacon, along with his friend Fred Egg, came up with a revolutionary breakfast. No? I don't think most people didn't even, what? Yeah, I just wrote it down. Francis Bacon came up with the scientific method. I mean, not that he developed, but he recognized it. He sort of formulated it. And, of course, it becomes standard practice then of what scientists do. The scientific method is built upon induction, inductive reasoning, rather than deductive reasoning. Not that there's anything wrong with deductive reasoning, it's just not very scientific in its approach. Well, what's the difference between induction and deduction, you ask? I'm glad you asked. Here's deduction. Deduction, you go from the particular to the general. You start with a syllogism. Number one, all professors are mean. Number two, Dr. Wineland is a professor. Ergo, Dr. Wineland is mean. Now, if premise 1 and premise 2 are correct, then our conclusion is absolutely true, always. Question is 1 and 2 always correct? That's deductive reasoning. Nothing wrong with deductive reasoning. This is the kind of reasoning Plato used. But you got to remember, it starts with, these presuppositions. If both those presuppositions, both those statements are true, the third one must be true. Okay? So you can get absolute answers with deductive reasoning. Inductive reasoning, more like what Aristotle would do. You go from the general to the particular. So how would we do this? Well, it's kind of a weird example, but let's try it. We would have to figure out a way to measure professors' meanness. I don't know how we would do that, but we would have to come up with a way. Then we go out and measure the meanness of 1,000 professors, let's say, or 100 or something like that. And then we go out and measure the meanness of 1,000 normal people that are not professors. Then we would have to compare it. Compare the measure of the meanness of professors versus the average of the meanness of normal people. If one is higher than 2, then we can say professors are meaner than normal people. Dr. Wineland is a professor, but does that mean he is meaner than normal people? Well, we don't know for sure. We could say there's a 90% chance that he is. So this is what science gives you. Science does not give you absolute answers. Science gives you percentages and means. Well, here's our buddy Francis Bacon. Besides making a mean Egg McMuffin, see that Francis Bacon is going to urge scientists to use the systematic approach he has developed, to use observation based upon generalizations. And when this takes off, we're going to see that around Europe especially, several scientific societies are formed. In England and in France, for example, the Royal Society of Science in England, the Royal Academy of Science in France. These academies would then bring scientists together. They would come there, they would have meetings, they would have discussions, they would share what it is they're working on, and by doing that, it would encourage them and it would bring new ideas. When I go to an academic conference and I share my ideas, my research, and there are other people there who have done other kind of research, maybe not exactly what I've done, but they'll hear what I'm saying and say, well, have you thought about this? Have you looked at this? What about this? And they begin to ask you questions. Because most of the time when I tell people that stuff, they don't care. But you get in a group with other people who are interested in it, and have been thinking about similar things, it can actually encourage it. And this is what makes science then become so, develop so quickly in Europe. Well, let's talk about this guy. Now his name is not René Descartes. How about René Descartes? Okay. Either way. 1596-1650. Now, he was, of course, greatly influenced by the Copernican and scientific revolutions. But the thing that he focuses upon is doubt. He comes to doubt everything. How can I know what it is that I know? How do I know it's true? He begins to doubt his own existence. How do I even know I exist? There's one account where he writes that he was looking at his hand, staring at it, wondering if it was real. So this is what I'm hoping this class does for you. When you leave here this afternoon, you'll go out and stare at your own hand and wonder, what have I done? Well, no, that's not what I hope. But he came to have this, de omnibus ditantum, doubt everything. Because he was a mathematician, so he said, well, at least I can believe that 2 plus 2 is 4. Or whatever. But then he said, oh, wait a minute. What if an evil genius has deceived me and has made things look like mathematics makes sense? And it really doesn't. So he finally has to come up with a way to overcome that. He works through all of it in his Discourse on Methods, 1637, where he says these famous words, cognito ergo sum, in Latin. Cognito, I think. Sum, I am. Ergo, therefore. I think, therefore, I am. Finally, Descartes came to the realization that since he is doubting himself and doubting these things, that he must actually exist. Because if he was being deceived like that, or if he didn't really exist, he wouldn't have thoughts that he wouldn't exist. I don't know. This is kind of like when they say, the guy says, oh, I think I'm crazy, and you say, hey, wait a minute, you can't be crazy. Because if you think you're crazy, crazy people don't really think they're crazy. They think everything's okay. Do you guys think you're okay? Or do you think you're crazy? Well, anyway, that's up to you to decide. By the way, Descartes also came up with Cartesian dualism. This is the idea that there is a body and mind that make up the individual and that they are not the same, but that they interface in the brain. So he said that your mind is running your body, much like a pilot runs a boat. He is sometimes called the father of modern philosophy. He also came up with analytical geometry, if you've ever taken that. But he sees identity as and mind and reason is not the whole organism. In other words, that who you are is not your body, but who you are is your mind, your thoughts. Well, I know. It's hard to get into this right now. Well, we got a couple more screens. Let's see if we can finish it up. We still have about a minute. So let me just put this up and I'll say a couple of things about it. We've already kind of talked about this. This is the idea that since God is consistent, then his universe will be consistent. So I'm going to move past that. And let me just introduce you to the idea of deism. Deism, then, is the idea that there is a God, but that God is not active in this world. God created the universe, He set up the rules, and then He winds it up like a clock, and then He just lets it go. This becomes the view of many. They reject a sort of biblical view, or Judeo-Christian view of God. They accept this view of God as creator, God setting up the rules, but God does not intervene. Therefore, you shouldn't pray. There are no miracles, anything like that. And eventually, people are then going to move to even more radical views, such as atheism, agnosticism, and atheism. All of these things then will come together in enlightenment, centered in Paris and in France, where intellectuals will gather in parlors and in intellectual clubs or salons, and they will share their ideas during Enlightenment. And this will really take off and grow. So built upon the scientific revolution, built upon this philosophical view, we're going to see then, and this is our last screen, that the Enlightenment is going to take these ideas and bring them out to all the people with philosophes who are traveling intellectuals who love wisdom. All right, we're going to leave it there for today. Have a good afternoon.